we can have bigger quivers, we can set any paths to 0. We can also further impose different relations. And then we can write down again an algebra, which is called path algebra with relations. Next. Yeah, so there's a nice, we have two really nice theorems in the literature, which relates to quiver theory. So if we have a basic connected finite dimensional algebra, basic means that we want every simple module over this algebra one-dimensional. So we want one-dimensional simple modules. Connected means that it's not the direct product of two, because we can analyze them separately. So if we have a basic connected finite dimensional K algebra, then I can find a quiver with an appropriate ideal, so that when I take the path algebra with respect to this ideal, namely the set of relations, this is isomorphic to my algebra A. So we can do it for any algebra. For any algebra, I can find a quiver. I can consider the path algebra with the relation that corresponds to this algebra. So this is very cool. And the second cool theorem is actually, if you want to study module category over this algebra, we can, this is also equivalent to category of representation over Q respecting I. So if we want to look at the module category of the algebra, we can look at the representations over this quiver and their equivalent. So here I noted admissible ideal. This is nothing fancy. The only requirement we will have is we don't want to kill arrows. If we want to impose this relation, we shouldn't kill any arrows in the quiver. So this is giving us a nice tool to study algebras and the module category of algebras. Most of the time in this talk, when I say a module, probably I will mean a representation over this quiver. So I did one simple example, A3 example. This is one of the popular examples we use. And if I consider, so this is basically my quiver. I had 3 vertex and 2 arrows. The spanning set will have E1, E2, E3 idempotents, paths of length 1. Let's say this is alpha, this is beta, and then paths of length 2, this composition, alpha, beta, or beta, alpha with respect to the convention we use. So it has 6 elements. And yeah, if I take the path algebra, then if I want to look at the modules over this path algebra, I can look at the category of representation, quiver representation. And this, in this example, it's very easy to list them. All indecomposable representations over this quiver are listed here. So for instance, this one, what I mean by this, I put a one-dimensional vector space at vertex 1, 0 to 2, 0 to 3, and then my linear maps are just zeros. So this is a representation and it's an indecomposable, namely you cannot really break this into further small pieces. I can take, this is also another indecomposable representation. I can put one-dimensional vector space here, one-dimensional vector space here, identity between them, and then 0 here, and linear map 0 here. So this is, again, another representation. So here it's easy to list all indecomposables. There are 6 of them. And as when we have modules have morphism between themselves, and this is true for quiver representations as well. There are morphism between quiver representation, and it's the and there's a map from this representation to this one, because I can embed this. I can embed this representation into this by just sending K to K, 0 to K, 0 to Z, 0, and this diagram would commute with these maps. So And yeah, by analyzing the maps between indecomposable representations, I can actually draw a bigger quiver. This represents the quiver of the category of representations over this graph. And sometimes we like to use dimension vectors of these representations. Basically, what we encode the dimension of each vertex space at every vertex. So for instance, this is 1, 0, 0, this is 1, 1, 0, 1, 1, 1, and so on. So this is just the representation by given by dimension vectors. And so yeah, the module category over path algebras, they're really well understood, and the study is using us on the Writing theory. Yeah, so then we can ask for which type of graph we have finitely many indecomposable representations. So for a given graph, we can find infinitely many or finitely many. So the classification is done. So it's the classification, the finite classification is done by using linking quivers. So I list them here. So AN, DN, E6, E7, and E8. So if we have a quiver, if we have a graph whose underlying structure is one of them, one of the listed graphs here, we can consider any orientation of those, then it's guaranteed that we will have finitely many indecomposable representation. So our category will be finite if we have any orientation of these quivers. And it's vice versa. If we have one of those, then we will have finitely many indecomposable. And this is the whole list. If you have any other quiver which is not in this list, we know that it will have infinitely many indecomposable representation. Okay, yeah. So this is the module category. Module category of an algebra can be understood using the category of quiver representations. So sometimes we like to work with a category bigger than the module category. So now I will introduce bounded drive category of a module category. So this is a bigger category. Our objects in this category are bounded complexes of modules, shown as depicted here, and morphisms given by, so we want to invert all quasi-isomorphs. And what I mean by this, if we have two complex and a morphism between them, and if their homologies are the same, given by this morphism, then we want to identify these two complex. So that when two complex has a morphism, and then if their homology are isomorphic induced by this map, then we call it quasi-isomorphism, and we want to identify them. So we want to invert all quasi-isomorphs. So these are the morphisms in our category. So I continued with the same example, A3 example. We depicted the module category of the path algebra over this quiver. Now I illustrate the bounded drive category. So of course, for simplification of the presentation, I just wrote them with the dimension vectors, and I ignore that they are complexes. So for instance, when I write 1, 0, 0 here, this really means that the complex which has this module corresponding to dimension vector 1, 0, 0 in the 0th degree. So these type of complexes are called stack complexes. They only have one module in the 1 degree and zeros everywhere else. So by each of these, I really means the stack complexes. And here we see a copy of the module category. So basically we can, from this example, it's clearly, we can clearly see that we can really embed the module category in the bounded drive category by just embedding this module to the stack complex. And then, of course, so this is a category of complexes. We will have any shift of any complex here. So this is a complex, and this is in the 0 degree. I can shift it. I can put this module into the 1 degree or -1 degree, and then we can, yeah, so then we can analyze again the maps in the bounded drive category. We will see that we will have module category here, and the shifted one shifted version of all these complexes -1, and it goes further. This goes to infinity. You will have 2 shift, 3rd shift, 4th shift, and on this side -2 shifts, -4 shift. And this is a more uniform picture of the bounded drive category of this A3. We have copies of mode A shifted by 1, shifted by 2. So that's a more uniform picture. So this is an infinite strip. So this is a triangulated, bounded drive categories are triangulated. Namely, we have triangles. So they look like this. So the idea behind triangulated categories is, instead of using short exact sequences, we want to use triangles of this sort. So we want to replace the role of short exact sequences with the triangles. So in homology, we take long exact sequences from short exact sequences. They are somehow fundamental, but now we want to change this role to the triangles. We have triangles. Actually, for every short exact sequence, we will have a triangle, and then we will create long exact sequences, and we will do homology by using triangles. So we have triangles in this bounded drive category. This is the triangulated category. This is the one of the important result we have. We want to work with triangulated categories. So this is a side note, just to give some motivation. So do maybe quiver theory. So if we take this quiver, 2 nodes with two arrows between them, if I consider the representation category of representation over this quiver, we know that this is infinite, that there will be infinitely many indecomposable representation, because this is not one of the types of the quiver we listed. This is not thinking. We have 2 arrows between 2 vertex. So yeah, we can consider bounded drive category, which is basically the same as bounded drive category of the module category of the path algebra over this quiver. And this is equivalent to the drive category of bounded complexes of coherent sheaves on projective space. So if we want to study this, we can actually jump here and then do some math over here, which I prefer. But this, even this equivalence actually is very, very general. This generalized to PN, coherent sheaves on much interesting spaces. And we can, then we change, of course, the quiver. Then maybe you will have a quiver, the path algebra with some relations, but this can be done very nicely. So this was just a quick motivation to the theory of quivers and actually use of drive categories. They are quite useful because these things are different if you look at them in the level of module category. So yeah, now we started with module category, then we take this bounded drive category. We want something larger than the module category, but then now this, in bounded drive category, we have this huge infinite strip. It's too big. So what we want to do, we want to take a quotient of this bounded drive category. Namely, we want to consider an orbit category of the drive category, which is now we come to the definition of cluster categories. So cluster categories, I will explain. They're introduced by Boan, and others in 2006. And so what is the definition of cluster categories? So we can take any path algebra over any linking quiver. So here the restriction is you have to choose your quiver, your directed graph from the list, which gives you finite representation type, one of the linking cases, A and D and or one of the E's. So we start with one of those. We take the path algebra over any linking quiver. We consider so now the class category is orbit category. We take bounded drive category quotient out by this functor tau inverse shift by 1. So in the example, how does this look like? Is so this was this infinite strip was the bounded drive category of A3, the quiver A3. And now what does functor, so we take this quotient, right? We identify some objects in the bounded drive category. And what it does really, so these are the honest, the purple ones are the honest objects in this quotient. And this blue one gets identified with this little guy over here. And this one gets identified with this. This one gets identified with this one. So if we illustrate it, I have this infinite strip. I identify two sides of this infinite strip, but this is somehow in cross fashion. Like this point get identified by this one. So then you get a Möbius strip actually. This is the cluster category. And I just write the fundamental domain of the cluster category. So here, this is the illustration of the objects in the cluster category. And we see we have the copy of the module category, but there's 3 extra guys in A3. So we have some extra. So we started with module category, we take the bounded drive category, and then we consider a specific quotient of the bounded drive category, and we end up with such a thing, which is called cluster category. So why do we do this? So this is not just a random construction. There's a reason behind this construction. There's a motivation. Why do we need such a category, which is a cluster category? So this is, cluster categories are introduced to understand something called cluster combinatorics, which are coming from cluster algebras. So look at the time, how I am doing with the time, okay. So now I will introduce cluster algebras and their combinatorics, but I will just start with a simple game, simple example. So what I will do, I will look at all possible triangulation of a pentagon.
I'm sorry, may I ask a question before going to the pentagon?
Yeah.
So, so A3 it's just SU4, yes? So, and when you write 1, 1, 0, something like that, this is just irreducible representations of SU4. And when you identify something and get Möbius list, what you mean by this identification on the level of the irreducible representation? So this I didn't get. So
okay, yeah.
So we have this on these circles. We have this 1 0 1 1 1 0 1 0 0. This is irreducible representation. I understand.
Yes.
So but then you identify somehow some of them.
Yes.
What means?
Yes. For instance, in this case. So what this functor is in type A case, especially in type A3, it's very easy. This is just again shift by 1. This functor becomes shift by 2.
Okay.
And then so what we are doing, so we have an object. So this object, of course, this has its dimension vector 1, 0. The module actually has this dimension. This is actually like this is an object in bounded derived category. So this is a complex. Having more.
Yeah, okay, yeah, I understand, but it's hard to think for me in terms of content. But it's just one irreducible representation of SU4. Yes, this is some irreducible representation of SU4.
Mm-hmm.
And
this one. So I don't know what you mean. For instance, for this object here in your setting.
But
right?
but in the beginning,
in my setting, this is just the two shift of this object actually, and then because of that they get identified, because I want to identify objects in the because this is a quotient, right? I have all the objects, but some of them get identified with respect to this functor.
I think what Dilara is thinking is in terms of Lie algebra
actually it's not
representation.
Dilara. I'm Ilmar Gahraman, so it's my. We listen all together, so I'm asking here.
So
I
thinking
listen with students.
Lie algebra representations, I think, but Emine is thinking about path algebras. And
yeah, I understand. But whenever we talk about the A3, so let's forget about the categories. But just pick one example. When we have A3, that's just SU4, and then we have irreducible representations of SU4, and then what we have these arrows. This is something between these maps between all this irreducible representation, if I understood correctly, yes. And then I try to understand how we. So of course I understand what means quotient, and then we can get something like maybe strip, but how we really do. I mean, if we have, I just want to see one example of what we identify with each other. So it's really, I don't know, and it's.
So for instance, like I don't know if I will this will clarify this, but so here, for instance, these are the projective representations and the corresponding stack complex, including these projective representations. Okay. And then here, this is actually, so this part will be for instance, if this is P1, this is P1 shifted by 1. This is P2, P2 shifted by 1. P3, P3 shifted by 1. So these are complexes. And then, for instance, this is the simple representation. This is coming from vertex 2, actually. This is the stack complex having the simple representation. And then this is the shift of simple at 2. So this is, if I call this S2, this is S2 shifted by 1. So these two objects gets identified because, I mean, maybe I'm like, I don't have time to give all the details, but I will be happy to talk about it later on, how we identify this on the level of module category.
Okay, thanks.
Okay, yeah, so yeah, now this cluster category is introduced because to study cluster combinatorics, coming from cluster algebras. So I want to start with this simple game. What I will do, I will start with a pentagon and I will consider a triangulation of it. Triangulation means dividing this pentagon into triangles, namely into UCGENs. So I use the title of the talk. So what I will do, I will assign variables. I will just assign one to all the boundary edges and 2 variables x1 and x2 to the diagonals. So I can find all the triangulation of this pentagon by just flipping the diagonal. So for instance, if I flip x2, I get this one, which is a new diagonal. And this, we should assign a new variable to this diagonal. So how do we assign these new variables? The rule is very, very simple. So if I have a quadrilateral like this, if I flip a diagonal, here it's E to F, this new variable will be A times C plus B times D over E. So that's my new variable to the new diagonal I created by just flipping. So in this case, so x2, I flip this to x3. This lies in this quadrilateral. And how do I write x3? It's just x1 times 1, which is x1, plus 1 times 1, 1 over x2. So this is my new variable. So I can keep going doing this until I get no new diagonal. So if I notice that if I flip this again, I get back to x2. And actually this rule I described as involution. So you will get back to x2 again. So then now I can flip x1. I flip x1, I get this diagonal here. This is another triangulation of the pentagon. And this is a new diagonal. I should assign a new variable to x4. So I don't know why these lines are appearing. Sorry about that. It might be the program I'm using. So x4, it's the same rule. How do I get x4? I look at the quadrilateral here. Remember, the boundary edges are assigned with 1. So this is 1. This is 1. 1 times 1 is 1. Plus 1 times x3, 1 times x3 over x1. So I do a simplification and I get this new variable assigned to x4. Okay, then I continue. This will be the last diagonal I will get. So if I flip this x3, I get x5. This is a new diagonal. And x5 will be described as follows. So I look at this quadrilateral. I just take 1 times 1, this is 1. This is 1 times x4. x4 was this, 1 times x4 over x3. x3 was this. So we see this is a little bit involved. We have to do some simplification. But it turns out something very nice. These two things cancels out and we get this nice new variable for x5. And if we continue, you will notice that if I flip this, then I get back to the one of the diagonals I started with, which is x2. If I apply this simple rule again, I will get back to exactly the variable x2. So here, two miracles happens. One of them is that, so in the denominator, if we started with x1, x2, two variable, we started to apply this rule, which is called mutation rule, actually. And then we get these new variables. But these new variables have always monomials in the denominator. I didn't get anything like 1 plus x1. It gets canceled out. So I end up with a monomial. And this is called Laurent phenomena. And you can, this combinatoric is not tied to the triangulation of angons. So you can actually take any angon, start with a triangulation, start with any triangulation, put variables x1 to xn, apply the same rule, we will get all these variables and they will be all Laurent polynomials. Namely, we will always end up with monomials in the denominator. So this miraculously, these things which are not monomial cancels out in the calculation process. And as I said, this is actually not tied to the triangulation of angle. This combinatoric actually is carried out into more general framework. And then this phenomena always happens. And then the other phenomena it happens is that positivity. So this rule is, I'm always adding and dividing. So you would maybe expect that, of course, we will always have positive coefficients for this variable, but it's not true when we think about, for instance, if I take x cubed plus y cubed, then this, when I express it as x minus y times x squared plus xy plus y squared, we see x minus y can appear if we do a cancellation. If we do a factorization and if things cancel out, x cubed plus y cubed actually can give us a negative, but this doesn't happen. So in general examples, we get these huge polynomials, rational functions, but somehow they work their way out very nicely, and then we always end up with positive coefficients. This is called the positivity phenomena, and it's proved in a very general setting. So this is basically, yeah, so what we did, we started with 2 variables and we generated 3 others. If we consider, the algebra generated by this 5 variable, then this is called cluster algebra. So, and then these variables we generated, they are called cluster variables. This 2 was the initial cluster variables, and then by applying mutation rule, we get these 3 other rules. So cluster algebras in general are subrings of the field of rational functions. The definition is simple. They're basically commutative rings, but usually commutative rings, we give generators and relation, we represent them like that. But here, the nice thing about cluster algebra, so the representation is we start with a set of distinguished elements generator, x1 to xn. We apply some rules, mutation rule, and we generate the others. So this is the combinatorics, the essence of the combinatorics the cluster algebras have. Yeah. So of course, yeah, we like a nice note. Maybe we have five cluster variables in this case coming from pentagon, and this is a Catalan number, and then you can guess that from sexagon or hexagon, then you will get the other Catalan numbers. The triangulations are counted by Catalan numbers. So in the triangulation case, the cluster variables, the number of them will be also counted by Catalan numbers. So in the thinking case, of course, if we start with a random, let's say surface, we can do it actually to any surface. We can triangulate, we can start mutating, flipping the diagonals, and we could get actually infinitely many cluster variables. But again, the classification theorem is done. We know when we get finitely many cluster variables. This is using the root systems related to Lie theory again. So we will have finitely many cluster variables if we are in one of the thinking case. Again, namely if we have finite root systems. So the cluster variables are actually into one-to-one correspondence with almost positive roots in the finite case. For instance, we get here, this example we did with pentagon is actually a 2 example. And we have 5 cluster variable, which in the A2 root system, we have 3 positive roots and 2 almost positive roots. So in, not almost, the 2 negative simple roots, this collection is called almost positive roots. And they are in one-to-one correspondence in the finite type cluster algebras. Yeah. So yeah, then of course we wonder the classification of finite representation type algebras is done by using again root systems. This should connect to representation theory. We should be able to get these variables using representation theory. So what are the corresponding objects in the representation theory to these variables? Can we do this nice combinatorics in the module category or some kind of representation category? So the first tries was the module category, of course, but this is not enough, because if we consider A2, the module category of A2, this quiver basically, will have 3 objects, 3 modules. So this wasn't enough. So the cluster categories are introduced to actually extend the module category a little bit to be able to cover this beautiful combinatorics. Basically, yeah, if you consider the cluster category over A2, we will have 5 objects. And people already explicitly described a map, which is called cluster character map, from this cluster, from objects of the cluster category to the cluster variable. So this map, I give this map to a representation, a module. The output gives me the cluster variable. So this is, of course, in the finite setting. These are all done in the finite setting, namely when we have finitely many representation, when we have finitely many cluster variables, finite root systems. Okay, another example I want to give, homogeneous coordinate ring of Grassmannians. So what we mean by Grassmannian, Kn, this is just k-dimensional subspaces of an n-dimensional space. We can consider the homogeneous coordinate ring of this space. This is functions on this variety. And then Scott in 2003 showed that the homogeneous coordinate of Grassmannian has cluster structure, cluster algebra structure. What we mean by that, in this setting, they explicitly describe what are the cluster variables, and they also get the combinatoric dynamics in the homogeneous coordinate ring of Grassmannians. Next, yeah. So, for instance, if we look at the homogeneous coordinate ring of two planes in an n-dimensional space, we can consider C to the n. We are looking at two-dimensional planes, and then we are taking the homogeneous coordinate ring. And this is generated by Plucker coordinates. So if you think of it as 2 by n matrices, the Plucker coordinates, what they mean, it's just the 2 by 2 minors. So the determinant of the 2 by 2 submatrices of the k by n matrices. So this ring is generated by Plucker coordinates, and these are all well known. These Plucker coordinates, they satisfy this relation. So the indexes looks quite involving when we first look at it, but if we draw this little thing over here, then it's easy to read. What is this relation? This is ik times jl. So this diagonal times this diagonal, ik times jl. On this side, we have ij times kl, ij times kl, plus il times jk. So this should now look familiar to you. This was the simple combinatorics we did in the pentagon, right? When we flip a diagonal, this was the rule to get to the new variables, which is exactly this relation, Plucker relation. So then you see that, of course, this ring should have cluster algebra structure. And then, yeah, in k is equal to 2k, it's proved by Fomin and Zolovinsky, and then it's generalized by Scott. So Plucker coordinates in Grassmannian 2n, the homogeneous coordinate of this, are one-to-one correspondence with sides and diagonals of an n-gon. And then we know that diagonals are in one-to-one correspondence with cluster variables. Actually, we can include the sides of the n-gon. We call them frozen variables somehow. They can come into the pictures, and then we actually recover all the Plucker coordinates. So each cluster variable corresponds to a Plucker coordinate. And then, of course, they satisfy the same dynamics, same combinatorics. So this is how I am doing with the time. Okay. So this is the recap. So let's look at it. Let's restrict ourselves to type A. So we have the cluster category, the objects in the cluster category. They also are in one-to-one correspondence with the diagonals of the triangulation of n-gon. So this is also one-to-one correspondence to the Plucker coordinates, and they are all in one-to-one correspondence with the cluster variables. So all of these things connect to each other in a nice way. So the joint work we did with Charles Paquette is that you can think the n-gons as a disk with finitely many points, right? So what if we take infinitely many points on a disk? So what happens, how the dynamics changes, how the combinatorics changes in this case. So what we want to consider is we want to consider a disk with infinitely many points, but we have some restrictions. So we want this infinitely points to accumulate to some accumulation points on both sides. So if we have such a configuration, this is what we want. We want infinitely many points, but we want them to accumulate in a fashionable way. So on. And then actually the category, the category which captures the combinatorics is described by Igusa-Tororo in this case. So for instance, this is called discrete cluster category. So the objects are actually arcs between the mark points on the boundary of the disk, but their categorification doesn't involve arcs between accumulation points. They only consider the arcs between mark points on the boundary of the disk. And they have corresponding objects for these arcs, and they describe morphism simply by arc crossings. So if we have M and N cross, if we have two arcs crossing, they have non-vanishing X, namely they have non-zero homomorphism. M to N shifted by 1, this homomorphism is non-zero. So non-vanishing X spaces is captured by the crossing of the arc. So if, for instance, this is one of the popular thing to ask in mathematics, we want to find a collection of objects which has zero extension. So X1 space is 0. And then actually with this description, we can visually describe all the class of objects which has 0 extension. And they have a specific name. They form a subcategory. So their category, discrete cluster category, it's also triangulated. We have shift functor basically shifting the arc clockwise. And then the triangles are explicitly captured by just looking at these type of configurations. They can write down all the triangles in this discrete cluster category. So these were already introduced, but what we wanted to do with Charles Paquette is that we want to include these arcs. They can go from one accumulation point to another accumulation point, or one accumulation point to a regular mark point. So we wanted to include limit arcs. We wanted to introduce a category which is bigger than the discrete cluster category, so that we have objects corresponding to these arcs as well. And the technique we use is that, so we took this disk, we did some surgery, we extended for each accumulation point, we insert an interval with so Z many infinitely points on this side, Z many infinitely points in this side, accumulating, because we wanted to keep this property that every accumulation point has two, on both sides they have points accumulating to them on the left and on the right. So we extended it a little bit, and then we consider this discrete cluster category. This is, again, we can consider all the arcs between any mark points, including these little intervals we introduced. And so this is a bigger category. This is again a cluster category. We just throw in some more arcs. And then we take a certain Verdier quotient. I'm just picturing the construction, but there is a algebraic construction. We introduce the multiplicative system, and then our multiplicative system is compatible with the triangulated structure of the category, so that we can take this quotient. Yeah, so there is a specific quotient we took, and then we identify some objects. Here, this then in this Verdier quotient, we found objects that correspond to these limit arcs. So we call it C bar, and this is our new category. We completely describe the structure of these new categories C bar. You can somehow think of it, an example would be like Grassmann to infinity, but this would be just an example of of course, like one can match the combinatorics. And so this is more like Grassmannian to infinity. And then we did this nice cluster tilting subcategories. So you can think of them again. The X1, so in the subcategory, we have objects that has no extensions. So we classified all these categories, which are subcategories, which are used to describe the cluster dynamics. And then we explicitly give a cluster character map in the setting. So I will end my lecture here. Thank you very much. I hope I didn't go over time a lot.
No, perfect. Thank you, Emine. That was actually perfect timing. Any questions from the audience?
Hi.
Hello.
Hello.
So I wanted to ask you about this mutations, that flips that you were talking about. When you talk about triangulations, you always talk about the specific ones where you, your triangles have their vertices on the polygon, I guess, right? This is, and you said something about mutations. Is this somehow related to this combinatorial mutations of polytopes that, for example, Kaspersky, I think, is working on, like that you have a mutation between two polytopes? It looked very familiar for me, that what you're doing with this flips, that if you have, let's say, two polytopes and you can define this combinatorial mutation, this also relates to a deformation of the associated toric varieties and this kind of stuff. Is it like somehow?
I think this is related because I know that people do this kind of stuff in toric varieties.
So this is the same type of
I'm not sure the references you mentioned, but so I know that there are similar constructions in toric varieties.
Okay.
But so for instance, if I have a polytope, two different polytope, so what are you mutating? Are you mutating planes or?
You are mutating somehow, like, I also don't remember exactly, but if you think it in the 2 dimensions, somehow cutting some part of the polytope and adding a new edge or facet to that to get a new one, like somehow or dividing this polytope into 2 pieces and changing the right side, let's say, with 2 new facets to get a new polytope. Like, there are many rules to do that, but you're definitely changing the polytope a lot other than the triangulation only.
So this, I mean, so what, the one of the insight is that, so you have, so what you have a collection, you're taking off one object and you're replacing it with another. Right. So in this case, you have diagonals, you're pulling out one diagonal, putting in another diagonal. So in representation theory, we were looking at similar structure. We wanted to consider a direct sum of objects. They have a certain property. They have x1, their x1 space is 0 between them. And then we were trying to do the same thing. We take one of them and can we replace it with another? So this is the general philosophy behind that, and so I'm not familiar with the other references, but if it's something like so you have a collection, you're taking one object and then throwing in another, and then you have some nice combinatorial way of describing this. It sounds similar.
Okay, thank you.
And I know that the cluster theory right now, it's like, it went beyond, I think, what they expected. They found cluster algebra structure in many different areas. I know in algebraic geometry there are these varieties, and now they introduce cluster varieties and so forth. It's very popular in algebraic geometry too.
That's also somehow kind of related to degenerations of weighted projective planes.
Yes, that's true.
This is, you can do also this mutations of polytopes, for example. That's why I was, that's cool. Thank you.
Thank you.
Emine, can you tell a little bit about the classification of cluster tilting objects?
Yes, so this is so in this example, you know that these diagonals, the set of every pair here is a cluster tilting object, right? They don't cross, so they don't have any X space between them. Does this sound
Yes.
good? Yeah. And then in this infinite setting, what we wanted to do, we wanted to do the same thing. We have infinitely many points, and then we draw arcs. And when these arcs doesn't cross, then they should be in the cluster tilting subcategory, right? So for instance, let me draw. So if in the simplest example, so if I have only one accumulation point and the infinitely many arcs, infinitely many points, the cluster tilting subcategory in this case looks like a fan. So we have these arcs, non-crossing arcs. I'm not drawing them nicely, but these are non-crossing arcs accumulating to their endpoints are accumulating to this accumulation point, and then we include this limit arc which goes to the accumulation point. So this is, for instance, the illustration of the cluster tilting category. The objects in the category which corresponds to these arcs have no extension, so that they form the cluster tilting category. And in the general setting, if we have more than one accumulation point, we have the same picture, we just copy and paste it. So it's the fan, we call it fan triangulation. We should have fan triangulation to be able to get cluster tilting subcategories.
Okay, thank you. Any other questions? If there are no other questions, let's react again to Emine and let's clap one more time. Oh, Ilmar. I think let's end the talk here, and Ilmar can ask questions separately to Emine so that we don't keep all the audience here for another 5 to 10 minutes. Okay.
Thank you for joining.
Thank you.